Test, test.
Hello, everyone. Welcome to Astronomy on Tap. We are sorting out the microphones, but in the meantime, if you want to play trivia, then please come get a trivia sheet and a golf pencil from Sam at the front, and we'll get started soon. Thank you so much. That's a weird sound. It kind of depends.
The only problem I found, I like them a lot too. The only problem I found, yes,
Hey, I got it. Woo!
it's not 100%.
I mean, we're not gonna say woo until it's over, but I think we might.
Because they're pink,
That's pretty
they
I
good.
think that's pretty
reflect in
good.
my eyes,
All
so
right,
I constantly look like I'm high or I have pink eye.
all right.
Because I know
Well, you
kids,
know,
it
you're
looks like
dealing with
pink eye.
space. Sometimes things, go wrong, right? Oh, we fixed it. Thank you all for coming out again tonight. I know we had some hail a little bit ago, but thank you all for making it out. And without further ado, I think Megan's going to come up here. No,
Not yet.
not yet. Oh, she's not coming up. No, not yet. Oh, you're still getting it together. I really don't have anything interesting to say unless it's about beer. Does anyone have questions about beer? I can answer that while we're waiting. No? Wow, that's good. Well, I'm going to call you up on the stage really quick now. Yes. I am the brewer of all the beers. Yeah, small things that you're like, well, that's going to sell, and then no one wants it. So, yeah, things like that. Okay, without further ado, I'm going to try to get the buzz going.
All right, let's give it up for Frank.
Yeah, Frank.
Beer on tap will be coming next month. Okay, can you still hear me? Hello? Hello? Okay, so now, sorry, this is really distracting for me. Okay, so, is it changing as I'm talking? Okay, okay.
Worse.
Well, I'll just project. So, welcome to Astronomy on Tap. We have another fabulous, thank you. Yeah, you can applaud for that, absolutely. Why not? So this month we have an exciting couple of talks for you. I'm just going to project. That's okay, take your time. This month we have an exciting couple of talks for you. Both of our speakers are actually affiliated or friends with the Data Intensive Research Astronomy Center. Is that right? Close enough. DURAC at the University of Washington. So they deal with large big data, lots of processing, and I'm sure you'll learn all about it tonight. But before we get to those talks, we're going to start Astronomy on Tap out like we always do, which is with 10 trivia questions. So if you did not get a trivia sheet and you want to participate in trivia, you can come grab one from Sam now. But for those of you who may not have done trivia with us before, how it works is I'm just going to put 10 questions up on the screen in order. Are you waving? Oh, okay. You will have 30 seconds for each question before I flip it to the next one. And then at the end, I'll go back and show you all of the questions over again, but that time only for 15 seconds apiece, okay? Are we ready for trivia? Yes. Good. The yeses win. So I'm going to get started. It's a good thing I didn't introduce the speakers. Yes. I was told that you are the running gag for today's trivia, so buckle up. Yeah, absolutely.
Try that. Oh, yeah. There we go. I think I might have got it this time. Go, Simcoe, go, go. All right, there we go.
I am going to introduce our first speaker of the evening. Dr. Jack Orlowski-Scherer is a staff scientist at the University of Pennsylvania. He's interested in cryogenic instrumentation, large-scale structure in the universe like galaxies, and recently, asteroids. And tonight he's going to tell us about asteroids, what they're made of, are they made out of things? I don't know, but I imagine that Jack is going to tell us. So welcome, Jack.
Yeah, thanks for the introduction, Megan. It's really nice to be here. It's my first time in Seattle, so it's a great introduction to come out for AOT. I love AOT. Yeah, and I'm going to be talking about asteroids, what they're made of. That hopefully by the end of the night you'll have some idea as well. So I just want to start by shouting out the people that I worked on this project with. So I'll be giving a general overview, but I'll also be talking a little bit about my work specifically. And I couldn't have done it without Rico, who's in Sigurd, and Nicholas, three of my people who worked closely with me on this project, as well as my whole collaboration. So we're going to start by talking about the solar system. And we're going to talk about the solar system because asteroids are sort of tracers, we like to think of the solar system history. So the solar system starts as a sort of big ball of dust and gas. And that ball of dust and gas collapses to form a what do you call it? Like a plane thing. Yeah, plane. Kind of like how if you take a pizza and you throw it up in the air repeatedly, it flattens out and goes from a ball of dough into a pizza pie. Disk. Thank you. There we go. And so at the very center of this disk, you form the star. And then in the outer regions, you form planets. You form protoplanets. And the way you form these is you start with very small objects. You start with just grains of dust hitting each other, and you make little rocks, and little rocks collide and make big rocks, and then big rocks collide and make really big rocks, and those make little planetesimals, and then those collide in huge collisions and make the planets that we have today. And then those planets clear out their orbital path, right? So what makes Earth a planet and not Pluto a planet is that the Earth has removed all of the material that is not Earth from its orbital tract, and Pluto hasn't. And so if you're in the orbital tract, you kind of have two options. You can either collide with the planet and become part of the planet, or you can get slung out. So essentially, you'll interact with the planet gravitationally and end up in a new orbit. These other objects then end up coalescing into a belt, and they form the asteroid belt, which is what I'm primarily going to be talking about today. But they also form the Kuiper belt and the Oort cloud, which are other reservoirs of leftovers from planetary formation. So what you're looking at here is a really amazing image. This is actually a protoplanetary disk around another star in our galaxy that we've resolved with a very incredible instrument called ALMA. And so that very bright bit at the center there is the star. That's a cloud of gas that's forming around the star. And then this more extended emission that you're seeing is the protoplanetary disk. And inside there are growing small planets. So this is sort of a pictorial picture of what I just described. You start with sort of a ball of gas. It collapses and flattens into a disk. You get a star at the middle. You get these planets that start to clear out the rings. And then after a long time, you've got your planets, and then you have the leftovers, which are the asteroids. So one of the reasons that we care about asteroids, I mean, they're interesting in their own right, but one of the reasons that we care about them is because they're really sensitive to the formational history of our solar system. So if you have a theory about how our solar system was built, how it developed, how it evolved, then it'll make testable predictions about the sizes of asteroids, about how many of a certain size you see, and about their composition. So what material, how much metal, how much dirt, etc., stone goes into the asteroids. And so if we can measure these things, then we can go and test our theories about solar system formation. So the asteroids have sort of they don't have as complicated of a sort of geological structure as our Earth does, but they do have geological structure. So at the very center of the asteroid, you have a core, which can be metal or not, and then you have sort of progressively more broken stuff. But the thing that I'm going to focus on this talk is at the very top you have what's called the regolith. So surface of, that's a fancy word for the surface of the asteroid. So the surface of an asteroid is not like the surface of the Earth, right? You step onto dirt and it's fairly hard and compact and you don't sink into it. The regolith of an asteroid is in terms of its like feel a lot more like snow. It's loose, and if you stepped into it, you would sink down until you reached the lower level of the asteroid. And it's not very well understood. The issue with the regolith is that for asteroids that come and land on Earth, which I actually get this wrong all the time. I think they're meteorites, but I'm sure someone can correct me. The regolith all burns off before it makes it to the Earth, and so we can't. It's really hard to find out about the regolith. And our ignorance of the regolith at one point was so steep. So the moon also has a regolith. Basically, every non-planetary body in the solar system has a regolith. And it was not known when we flew to the moon how deep the regolith was. There were theoretical expectations, but no one had been there. So obviously, we didn't know for sure. So if you've ever seen the Apollo moon lander, it has very long legs that come down. And they have a ladder that they've got to descend from the cabin to get down to the surface. That's partially for shock absorption. Those big legs help absorb the impact of landing on the moon. But it was also partially a hedge against there being like 2 feet of regolith on the surface of the moon. So there was a fear, not particularly likely, but a fear that there'd be like 2 feet of regolith. If you had a very short legs, the lander would actually get stuck in the regolith. And so they put these long legs on. It ended up only being about an inch or two, so it wasn't an issue. But we didn't know that before we went. And so the regolith, very mysterious. Part of the reason why is, the other reason why is that it's very hard to pierce into the regolith. So we can observe asteroids in the optical, but when we do that, the only thing that we see is the absolute very surface of this regolith. So it doesn't really tell us about what's going on in the middle here. And the solution to this is observations in the microwave or millimeter frequency ranges. Because the regolith is so loose, it's actually partially transparent. Kind of like a plastic in that way. And so you can see a little ways into the regolith when you're looking in the millimeter or in the microwave. Sorry, to be clear, those are the same two bands. It's just millimeter is the wavelength, and microwave is the frequency. It's the same light. And that allows you to essentially like X-ray, I shouldn't say X-ray because that's also a type of light, but it X-ray, in air quotes, the regolith. And so that's what my colleagues and I have done. So like I said, there's a couple different ways that you can look at them. You can look at the asteroids that crash into Earth. The problem with these, of course, is that you lose all of the information about the surface. It burns up. It's also very biased, right? Very small asteroids burn up entirely before they make it to the surface of the Earth. So you only study big and preferentially metallic asteroids. You can visit them with spacecraft. This is great. This is actually this is a video of a comet, not an asteroid, but it's dope. So sue me. But you can fly a spacecraft to them, and you can get sweet data like was taken by the Rosetta mission that took this video. The problem is that that's crazy expensive and really only practical for a very small handful of objects. You can go to like 2 a decade if you're lucky, right? So you don't get really good statistics on them. And then you can look at them with telescopes, which is relatively cheap, and you can look at as many asteroids as you want, or at least as your telescope will allow you to. However, you have to do a lot more work to figure out what you're seeing. So just to go back to the sweet movie again, what you're seeing here is the actual surface of the asteroid. That's some sort of cliff. This comet, they believe, was formed by a collision between 2 other comets, so you're seeing kind of the valley between the 2 bodies. This stuff all sort of moving coherently down. is actually the night sky. So this has been sped up a lot. So what you're seeing here is the night sky passing. This is a couple hours. But then all this stuff sort of whizzing around is it's not exactly regolith because it's a comet, but it's similar to the regolith. It's like the comet regolith, so to speak. And that would be similar to what you would see on an asteroid as well. This is what you do actually see on an asteroid. I actually didn't write down what asteroid this is, but this is a asteroid. This is from a optical to IR image taken by a spacecraft that went and visited one. And you can see all these rocks as well as the stuff around it, which is the regolith. Like I said previously, you can look in the IR. And that tells you a lot about what's happening at the immediate surface, but has no ability to penetrate the surface. You can look in the radio. So the asteroids don't actually emit in the radio, but what you can do instead is sort of like a radar where you send out a radio wave, bounce it off the asteroid, and then look at what comes back. And that tells you a lot about the shape and the spin of the asteroid, a lot about its dynamics. And then you can look in the microwave. And this is sort of allows you to take a peek into the surface. So in the IR and in the optical, IR infrared, if I didn't say that, this tells you a lot about the temperature at the surface of the asteroid as well as its reflectiveness. So asteroids in the IR and optical are doing a combination of reflecting light and emitting light. The reflected light is light from the sun that comes from the sun, and it hits the asteroid. And the asteroids, we wouldn't think of it as shiny, but it's actually a little bit shiny, and so it reflects some of that light, and that comes back to us, and we see it on the Earth. And then it also emits thermally. So every body that has above 0 Kelvin, which is all of them, emits some amount of light intrinsically. This is why the sun shines and why like hot pieces of metal shine. And so we can observe this, and then essentially like the amount of these two different lights that you see tells you a lot about the surface materials of the asteroid. In radio, like I said, the asteroids don't emit in the radio, but you can bounce radio waves off of them and take a look at them. So this is Arecibo, a huge dish that unfortunately is no longer in operation. It collapsed like 4 years ago now, actually. It's been a while. But it used to be sort of the premier facility for doing these sorts of observations of asteroids. And so what Arecibo does is it sends out a signal. That signal goes out in outer space, it hits the asteroid, and then different parts of the signal reflect back at very slightly different times because of the shape of the asteroid. And then you look for the echo, and you get this sort of smearing where you send out a blip, and you get back a smeared out blip. And if you're very clever, a lot smarter than me, you can figure out how that smearing maps back onto the shape of the asteroid. And then you can create really cool images like this. So Arecibo is towards the top of the screen in this picture, and it's beaming light down on this asteroid and reflecting off of it, and you can see that they can very clearly recover the shape of the asteroid that way. Even cooler, you can take videos. So here's an asteroid spinning. And so this is also interesting because people are interested in the dynamics of asteroids, so their spin rates. And you can also discover things like this little buddy, which is actually a moon of an asteroid. So that's a very, very small rock that's orbiting this asteroid. So now on to the meat of the talk. We're going to talk about what microwave brings to the table. This is ALMA. This is sort of the premier microwave facility for studying asteroids. ALMA is an interferometer, which means it uses lots of telescopes to make a sort of mosaic image. So each of these telescopes takes an image of the object of interest, in this case an asteroid, but it looks at lots of things. And then we very cleverly combine all these images, and we end up with a much finer resolution image of the asteroid than we could otherwise. ALMA has very high resolution and very high sensitivity, which means it can see very faint things. It has a long history of looking at asteroids. And in general, what it has found, there are other instruments that do this as well, almost just sort of the big name and also the most photogenic. And what we found is that the asteroids are not as bright as we expect. So we have all these measurements in the infrared and in the optical, and they tell us about what the material properties of the asteroid are and how hot the asteroid is. And we have a pretty good understanding of how black body emission works, so we can make a prediction for how bright they should be in the millimeter. And that prediction is consistently significantly more bright than what we actually observe with our telescopes. And so what that's indicating is that the surface properties, right? Remember how I said the IR is only looking right at the surface, and with the microwave, we're sort of peeling back and looking into the asteroid. That's telling us that the properties in the asteroid are changing in the regolith, which is really interesting, what we're trying to get at. And so, you know, ideally, what we'd be able to do is take these observations and pin down what's changing in the regolith. The problem with this is that ALMA observations take a really long time, and everyone and their mother wants to use ALMA. It's like one of the, outside of this, I'm fairly certain it is the most oversubscribed land-based telescope on Earth. James Webb and Hubble are more oversubscribed, but ALMA is oversubscribed by something like a factor of like 9, which means they have requests for 9 times more observing time than they are actually able to give out. ALMA, like, you have to have really good science to get ALMA time. And so, you know, we would like to alleviate the demand on ALMA a little bit. And that's where my experiment comes in. This is actually not my experiment. Once upon a time, this was my experiment, but it hasn't been for a while. This is a South Pole telescope. The South Pole telescope is what's called a cosmic microwave background survey experiment. I'm not going to go too crazy deep into what that is because that's actually dust in our galaxy, but that's sort of what it sees. I'm not going to go too crazy into what all that means, but the sort of key word here is microwave, right? Microwave is the frequency of interest. And what these telescopes do is they just go back and forth and sort of scan. They just scan the sky nonstop, and they let the sky pass through them. And in doing so, they map the whole sky. So they don't really look at things, they're looking sort of at the whole sky. And they've been observing for a very, very long time, so they have very good sensitivity. So if you're clever, right, because these are microwave instruments, they weren't built to look at asteroids, but if you're clever about doing the data processing, you can actually get asteroid images out of them. So the SPT was the first experiment to try this. They detected 3 asteroids in their data. Now, SPT is an excellent experiment. They have really great sensitivity, and they know what they're doing. 3 might be slightly disappointing. And the reason is actually kind of just, well, not SPT's fault in some sense. SPT, as the name suggests, is at the South Pole. And so the SPT can only see fairly low on the sky, right? It can only see things that are sort of visible from the South Pole. Most asteroids live in the asteroid belt, and the asteroid belt is in the plane of the solar system, which is more or less perpendicular to our rotational axis. All that means is that when SPT is looking, right, the plane of the asteroids are all here, and SPT is looking that way. So it's looking completely in the wrong direction to see these asteroids. So really what you want is an experiment that does what SPT does, but is closer to the equator where it can observe the asteroid belt. And astoundingly, such an experiment exists. The Atacama Cosmology Telescope is the experiment of which I'm a member. It's located in the Atacama Desert in Chile. It's up in the north of Chile. It's very high there, and it's very dry, which is why the experiment was originally put there. But it also happens to be reasonably close to the equator. And as such, it can observe the asteroid belt. We also have 15 years of data, so tons and tons of data in the can to go back and look for these things. And it has 3 different frequencies of observation, which is really interesting because those 3 frequencies actually probe slightly different depths into the asteroid, right? The sort of opacity of the regolith is tied to the wavelength that you're observing at, right? Remember I said the IR, it's opaque. As you go to lower frequencies, it gets more transparent, And so different frequencies see different depths in. And so we have all this data, and the question became, how do you get the asteroids out of the data? So to do that, you have to understand, how we do that, you have to understand a little bit about how we observe. So our telescope is not like what you're probably used to thinking of a telescope operating like. You're probably used to thinking of like Hubble or James WST, James Webb, or maybe if you're frequent of these talks, DES or LSST. All of these telescopes work the same way, where they point somewhere in the sky, they open their shutter up, they take a picture, and then they close the shutter, and you get a bunch of still images in exactly the same way that a regular camera takes an image. What we do is instead to just continuously scan the sky. And so our data, it's more like a video. It's more like a video of what you would see if you were looking at the sky and just dragging your camera back and forth and back and forth. So as you can imagine, it's already kind of difficult to figure out what the static image of the sky is when you're taking this video and dragging it back and forth. Essentially, what we have to do is to figure out what frame the asteroids are in, right? So one thing I should clarify, these are all asteroids that are already known about. We don't detect asteroids. These are all detected in other bands, and then they have their orbits. And so we can use that orbital information to figure out where the asteroid is at a given point in time. And then we can go clip out the frames that have asteroids in them. And each of those is a picture of the asteroid. And then we can extract our data from all of these pictures of asteroids. So to give you a sense of how that works, to scan, we basically go back and forth like this. And as the sky passes through us, right, we end up with essentially different pictures of the sky, right, because of the drift of the sky. So it looks sort of like in the frame where the sky is fixed and we're moving, you can see that by our back and forth motion actually gets converted into this sort of ladder-like motion across the sky that allows us to image the entire sky while never really changing the pointing of our telescope. So in order to get the, and here's another image showing exactly the same thing. This one's a little more schematic and complicated, but you can see the same idea. These lines are our telescope scanning back and forth, and you can see that as the day goes by, we scan different portions of the sky, and eventually you get around and you're back where you started. So you do end up with a picture of the whole sky. So you can go ahead and do that. You can take all these pictures, and what you end up with is essentially a video that looks like this. So this is no longer preliminary. I just couldn't find this GIF without the preliminary text on it. But this is an asteroid, or closer to a minor planet, called Ceres. And this is a video of what ACT saw when we sort of took all of these still images that we had collected over the year of Ceres and lined them all up and then played that video. So a little bit of a time scale here. This is each time it gets brighter and dimmer, that's about a year. So this has been sped up considerably so that we can get out of here on time. So you might be asking, why is the asteroid blinking like this? Mostly what's happening here is we're moving further away from and closer to the asteroid, right? So as we orbit around the sun, during one part of the year, we'll be very close to the asteroid, and then at the other part of the year, we'll be on the other side of the sun from the asteroid, and so it gets a lot fainter and a lot brighter when that happens. Luckily, we understand the physics of this exactly, and so we can remove that effect, and we can end up with sort of the intrinsic, or if you're familiar with optical astronomy, the absolute magnitude, so to speak, of the asteroid. So we go ahead and do that, and you end up with these still images of an asteroid. So here we've removed this apparent blinking of the asteroid, and we're left with sort of the true brightness. These are actually SPT asteroids. You can see it in the picture here. And what these give you when you have multiple frequencies is that you have, you have multiple frequencies, and you'll notice that the asteroid disappears in these two images and is fainter in that image. And that's because when we're looking at different frequencies, we're looking at different places in the thermal spectrum. Just gonna quickly move by that. The details of this spectrum aren't too important. The only thing that's really important is that we know the shape of this spectrum exactly. It's well understood. And so if you have a deviation from that spectrum, then we can detect that and interpret it as something going on in the regolith of the asteroid. And our data does indicate that. So we find consistently that there's less flux than you would expect again. And so the question is, what's going on under the surface? And the answer is somewhat anticlimactically is we're not totally sure yet. We're still working on this problem. One sort of hint comes from asteroid classes. So asteroids are grouped by their spectrum. So we look at the amount of light that we see as a function of frequency, and you can classify the asteroids. They have different shapes for their spectra. Those classifications correspond really well to the actual material composition of the asteroid. And here's where the answer to the trivia question comes in. So the two largest classes by far are C-type, which stands for carbonaceous. It means that they're very high in carbon. And S-type, which stand for stony, or if you're feeling fancy, silicaceous. And these are what they sound like. They're very stony asteroids. And so here's a couple of different examples. The S-type are up here on the left. You can see, even just by eye, that they're noticeably brighter. They're much whiter than the C-types, which are on the right, which are almost entirely black. And so a sort of question that you can ask is, okay, is the deficit that we see, does that change when we look at different classes of asteroids, right? Because if it did change, that would be an if we're able to say, okay, the deficit's a lot worse with one class of asteroid than another, then that would be evidence that the source of that deficit is in the material of the asteroids, which is different between the different classes. And we did that, and oh my God, that does not come, the colors do not come through on this projector. That's a bummer. But we did this, and the answer is essentially yes. They do map onto the classes, so you can go ahead and ignore these right too. And you don't need to know too much about what's going on in this plot, but just look at this is the amount of deficit for C-class. 0 is no deficit. So the C-class asteroids actually agree almost exactly with our expectation. In fact, within uncertainties, they do agree with what we expect to see from the IR and optical measurements. But the S-type asteroids disagree. They have much less flux than what we expect. And so this is pointing us to an answer. And again, unfortunately, I can't tell you exactly what the answer is, but it's pointing to an answer where something about the fact that these asteroids have a lot more carbon and these asteroids are a lot stonier is the source of this problem. We still have a lot of work to do to analyze the data that we have already. But we also have a couple of exciting new telescopes that are coming on down the line that are going to be able to improve on our previous results. I also work on an instrument, or on a telescope called Simon's Observatory. It's sort of a successor to ACT, and it's going to continue the legacy of ACT. So we're going to do exactly what we did with ACT, with Simon's Observatory. But Simon's is something like a factor of 4 or 5 more sensitive. So we're going to shrink all of our error bars by 4 or 5 and see a whole bunch more asteroids, which is really exciting. And CCAT Prime, which is a sister telescope to, that's a typo, it should say sister telescope to Simon's Observatory, it's going to perform a very similar survey. This picture is also a picture of CCAT Prime. They actually share the exact same telescope design. They just mount different cameras on the telescope. And it's going to be very complementary. It's at a slightly different set of wavelengths. So it's going to help us fill out this picture of what's going on in the regolith. So that's just about time. So I will go ahead and open up the floor for questions. Same spot. Let's see if I got that in the backup slides. That was Simon's as of about a year ago. It's actually there now. The telescope does exist. Sorry. This is what the site actually looks like. That's our camera. You can't see it, but ACT is like 100 yards behind that camera. So basically the same spot. Yes. Any other questions? In the back there. Yeah, my point of view is that I don't want to be mean, but like maybe there's a point in a physicist's career where they should be like put out to pasture. So yeah. Yeah, so that's my point of view on that. One thing that is really cool is we will be able to do studies like this on visitors from other extrasolar visitors. So ALMA is actually really well suited for taking a look at these things and understanding their composition. And this is particularly interesting because we don't really know how unique the composition of our solar system is. So when you look at things like this, you're actually getting a really unique peek into what else is out there and whether it's similar to what we have here in our solar system. So
The asteroid belt sort of remains of the accretion disk. What explains the difference between the different asteroids, like the metal-rich ones, the carbon-rich ones? If they form from a sort of a uniform disk.
yeah, that's actually a good question and a area of active research. I am actually the little subtext here is I'm actually not an asteroid. I'm not a planetary science person. I'm a cosmologist by training. But my understanding is essentially that the thought is that they probably differentiate due to the differences in density. So the metals and the rocks have different densities. And that probably leads to them differentiating spatially during the formation process. But it is still an area of research. People aren't 100% sure how that happens. So it's a very good question. It's something we're interested in. Oh, yes, absolutely. In the back there? Yeah, you. Yep. Yeah.
Potato and they aren't exactly super uniform, where it's like
Making good backup slides is an art. So the question was, do we see asteroids that are geometrically non-uniform? And if so, can we say anything about that? That's a wonderful question. We do and we can. So this is sort of what that looks like. You have an asteroid that's very potato-shaped, as you said. And so when we're looking at it skinny side on, the flux goes down just because there's less asteroid looking at us. And when we're looking at the fat side, we see more. And so you get this very characteristic 2F pattern where at twice the frequency of rotation of the asteroid, you get a modulation in the signal because you see the skinny side twice and the fat side twice per orbit. And we do actually see these. So this is an example. This is not labeled again, but I think that this is Procne, maybe. And that's exactly what you're seeing here. You're seeing a variation. So these green data points are individual observations. In the blue, we've binned them up together. And the phase down here is essentially the orbital. It's the orbital phase. So it's which point of the asteroid is facing towards us. And so you can see this very characteristic 2F thing. And so you can actually get the orbital period out of doing this if you're interested. most asteroids do not have a have a curve nearly this regular. They have features like craters and other sort of irregularities that dominate the phase curve with really sort of jagged-looking features. That's interesting in its own right, but it won't. Most of our asteroids don't look like this. They look like, you know, woo, like that. They're pretty flat, and then it goes flying off somewhere because I don't know. There's like some dark spot on the asteroid or something like that. Excellent question. Oh. Yeah, something like that. Don't quote me. Yeah.
That's like common for other asteroids.
Yeah, that's a good question. We have some idea, and the consensus seems to be that it differs, but that's not an unusual depth. Oh, sorry. The question was, I said that the moon's regolith is about 2 inches deep. Is that a common depth for a regolith? And the answer is, it's probably not uncommon, but the regolith depth is certainly not uniform. There are highly metallic comets or asteroids, pardon me, highly metallic asteroids that have almost no regolith, and then there are other ones that we think have several inches of regolith built up on the surface. Actually, interestingly, the amount of regolith is also something that's studied. So not just the composition, but the depth. It relates to the rate at which the asteroid experiences what they call it. They have a very interesting name for it. I'm going to blank on it, but essentially micro collisions, like very small bits of dust or whatever, hit the surface and essentially stop the regolith from compactifying. One more question. Go to the front.
Picture of the asteroid with the rocks on the surface.
Yeah.
Asteroids seem to be a collection of rocks found elsewhere. So where's the source of those rocks, and/or how big does an object have to be before it compresses the material to create the rock itself?
Yeah, that's a good question. So the question was, in this picture that I'm getting to of an asteroid, we can see all the rocks on the surface. Whoop. And so how big does an asteroid need to be to start collecting rocks? Is that?
Well, collecting and/or how big does an entity have to be to create rock?
So that's a good question. The follow-up question was, how big do you have to be to create rocks? And the answer is, they don't. They don't create rocks. The rocks end up on them. So the formational mechanism is that very early in the universe, you just have dust and little grains of sand or whatever. Well, not sand, but yeah, you have little grains. And they come together and they make slightly bigger grains. And then eventually you sort of compact together enough material that you form a rock. So none of these rocks are going to be, and I am now thinking geology, which I don't know, but there's like sedimentary rocks. They don't have sedimentary rocks. All of their rocks are formed by this sort of accretion process. And so you form these rocks, and so these rocks got here by colliding with the asteroid. They weren't like formed by geological processes in the asteroids. Some of the largest asteroids probably were geologically active at some point in the past, but the vast majority were never geologically active, and all asteroids today are dead. So basically any rock you see here is going to be something that fell onto the surface.
They weren't formed elsewhere?
No, they were a part of that same buildup process that builds the asteroid itself. All right. Thank you. People seem to like it.
Yeah, they did. All right. So now I am going to announce the trivia answers
Wait, what do I
and
have
trivia
this for if I
winners,
was speaking
and
at
then
the
we will
mic?
have an intermission.
What did I have this
before
for
the
if I was
second
speaking at
talk.
the mic?
So,
Thank you.
are you guys talking
Yeah,
to me
people
or
are
each
really
other?
engaged. I love it. I'm going to go grab my free beer.
Not me. Okay. So, anyways, trivia answers.
Apparently, I got a free beer.
Tim Davenport is not actually a third-year grad student, but he used
Could've
to
fooled
be
me.
a third-year grad student at UW. He is now faculty. The concentration of asteroids between Mars and Jupiter is the asteroid belt. 75% of asteroids are carbonaceous, as Jack told us. The first asteroid that
don't-
brought back samples
Was I
is
actually on
called
this, or was I just
it's
speaking? This
Takawa. The surface of asteroids is regolith, which you should all know very well by now. Astrometry is the measurement of position and the movements of stars. That's true. You can see only Jim Davenport. Because he is a star. No, just kidding. Less than 10,000. But Jim is one of those 10,000, luckily. Stereo does not make catalogs of stars, though Jim was quick to point out that Stereo does see stars on the fringes, although it is not its main purpose. Sorry, I did not rate the question. Okay. The Rubin Observatory is being built in Coquimbo. Thank you. Rubin is not actually a region of Chile, but I did have to ask this to be sure. It is, yeah. The Rubin Observatory is named after Vera Rubin, who's phenomenal. And finally, DIRAC stands for the Data Intensive Research in Astrophysics and Cosmology. Okay, so the trivia answers. We had a first place winner that got 8 questions right. And then we had a 4-way tie for second place with 7 questions right. So you will all get prizes. But wait until the end of the second talk to come get your prize. So I'll announce the second place winners first. We have Robin R. Who is that? Make some noise. Do something. Thank you. Good job. Okay. Skittlebugs. Skittlebugs. Okay. Good. Good. Buzz. And aliens. Yeah, well done. Okay, and the first place winner that beat all of you is Eckering. Good job. Okay, so with that, we're going to take a 10-minute intermission, and then we will be back with Dr. Jim Davenport, who was also here last month, and he will be our second speaker of the evening. Thank you. and food from the food truck. And everybody's ready to hear more science? Okay, so our second speaker of the evening, you know him, you love him. He was here last month. It's Dr. Jim Davenport, who is faculty in the astronomy department at the University of Washington. Although he was telling us about astrobiology and the search for extraterrestrial life last month, this month he has come to tell us a very serious public service announcement that there are too many stars. So with that, Jim.
I promise I'll stop coming after this. Did anybody answer all Jim Davenport to the quiz? Then you're the real winner. You're the real winner. There's too many stars. I think that's my message. In a Seattle, you can see, well, 1 plus or minus 1. Plus me. Yeah, that's right. But in general, there are too many stars. And I don't mean to say that, like, we need to get rid of them, like some kind of cartoon supervillain. But I'm just saying if we did, my job would be easier. This is my favorite map or image of the night sky. This is a picture taken by the Gaia Space Telescope of something like 1.8 billion stars in our galaxy. Every little dot, every little bright spot here is a star in our galaxy. Well, that's a lie too. These are different galaxies, but they're part of our galaxy. This is too many stars. We can't count all these. We can't study them all. We can't understand them all. This is too many. So here's a plot that I made in preparation for this talk, something that I'd wanted to see for a long time. This is a trivia question, so I'll ask it again to you. How many stars can you see, what we would say, with your naked eye, with your visible eye? Again, presuming we weren't in Seattle. Presuming it was actually dark outside and not cloudy. How many stars could we see? Less than 10,000. You could only see me. I would outshine them all. That's right. You'd see less than 10,000. Something, depending on where you are, something like 5,000 to 8,000 is the answer that you get usually. It's not that many, right? In antiquity, we would look up, humans would look up, and depending on the quality of your eyesight, you'd see something like thousands of stars. And there were probably, I'm not like a scientist of people, there were more than 1,000 people, more than 10,000 people on the planet. Somewhere around 1800, we started doing a better job of counting. Now, these are names of catalogs of stars. These are like, in the olden days, like literal books, just full of tables of stars, like their location on the sky and roughly how bright somebody thought it was with their eyeball. The brightest few hundred stars have like names, like Vega or Sirius or Betelgeuse, right? The very bright stars have names. And then at some point we start naming them with Greek letters like Alpha Centauri. That's the brightest star in the Centaurus constellation. And then we start getting down to numbers, and then we start getting down to just like phone numbers, big catalog numbers. But back here, back in the good old days, I'm not that old, but back in the good old days, we had like the Lalande catalog. This is a French catalog that had something like 40,000 stars. This was a major achievement. 40,000 stars in like 1801, before they could take photographic plates of the sky. They had telescopes. They could look at the sky, but they didn't have like a photographic archive. And yet they recorded the positions and brightnesses of like 40,000 stars. What an amazing triumph. It's good enough. That's enough. We don't need any more. That's enough. But a couple of Germans came along, something like 50 years later. This is the Bonner Durchmusterung, I apologize to anybody who actually speaks German, catalog. We just call it BD. They raised it by about a factor of 10. This is the Henry Draper catalog, right about the same number. They had a lot more information. Another 50 years later, they included spectroscopy, radial velocities, anything else they could learn about the star. So here around, like 1920, a century ago, we were at like 100,000 stars. This is plenty. This is plenty of stars. The Smithsonian Astronomical Observatory just notched that number up just a little bit. They moved up a little bit. I'm leaving a lot of catalogs out, of course. But there was this transformation. It started in the mid-90s with the Hipparcos mission, studying about 100,000 stars precisely, and then an accompanying mission called Tycho or Tycho. And so the Tycho 2 catalog, something like tens of millions of stars. We're already getting suspicious here. It's a lot of stars. We can't know much about all of them, right? Tens of millions of stars. And right around the year 2000, you see this like incredible ramp up. Now, I'm an astronomer, so I love logarithms, right? I love seeing things in log space because the universe is incomprehensibly big. I only understand things in like log size. So you were all like of order 10 to the 1 feet away from me. That's good enough for an astronomer. My car is like 10 to the 2 feet away, and my house is like 10 to the 3 feet away, and that's close enough. Right, these are orders of magnitude in size, right? And so somewhere around 2000, we make this like catastrophic leap upwards from tens of millions, 10 to the 6, to like 10 to the 8. This is like a huge problem. My job becomes a lot harder now. Now we have 300 million stars in the 2-micron all-sky survey. And in the US Naval Observatory Catalog B, 1 billion stars, 1 billion objects. There's some galaxies hiding in there. We'll give them a pass tonight. Something like 1 billion objects. Right around 2001, we hit 1 billion. Thank God this stopped. We've been right at 1 billion now for something like 20 years. This is a lot of stars. What happened in the year 2000? Computers. Ah, yeah. I mean, like computers were, for the young people in the room, computers were invented before the year 2000. But computers started to get really powerful and really cheap, and we all started to have the internet. And so we started having a great need to send each other catalogs of data. Now, I will say, USNOB, this catalog here, was only available either through if you knew a friend who had it, or if you sent away for a box of CDs. But it was a very important catalog. We still use it today, more than 20 years later. So this image that I showed here, this beautiful image, pristine, incredible map of our slice of the galaxy by the Gaia Space Telescope, that came out just a couple years ago. I actually came here to Astronomy on Tap to tell you all about it, so I'm sure you all remember. This is the Gaia Data Release 3. This is 1.8 billion stars. That's plenty. We don't need to be greedy, guys. That's plenty. We could stop here. But astronomers are never satisfied. Because the more we keep studying stars, the more we learn about the stars, let's be honest, the less we think we actually understand. And so we're about to take this huge leap forward again. Well, I mean, it's not 10,000 to 100 million, but we're about to take a really, really important leap forward. And I'm super worried about it, guys. Starting in about 1 year, the Rubin Observatory, which you have already heard about, located in the mountains in Chile, in beautiful desert above Chile, is going to observe something like 17 billion stars in this galaxy alone. The Milky Way has something like 400 billion stars in it. We're going to observe a large fraction of it. Let's fall off the edge. 17 billion. And about that many galaxies as well. We're going to have catalogs of 40 to 50 billion things we got to deal with. This is a lot. For comparison, the population of this planet, while it is increasing, and that's a good thing, it's going up. We hit around 1 billion people right around the turn of the 1800s. We hit about the first billion, the second billion almost a century later, and then we've been on a steady march upwards. 10 billion will happen somewhere in the next, 30 years. Again, I'm not a people scientist. I'm a star scientist. The Rubin Observatory, this catalog of stars, will for the first time observe and catalog and record the brightnesses and positions for more stars than there are people on this planet. And to me, that seems like a fundamental change in how we think about the universe, how we think about the stars in our galaxy. We have to start thinking differently about how we do astronomy. So a new era in astronomy is here. And it's transformed every other science, and it's transformed this city, and it's transformed, I think, a lot of our lives, and you all have supercomputers in your pockets now. But this era of computational, data-driven astronomy is here. We're already here. We've already let this genie out of the bottle, unfortunately. We don't have the luxury of getting to know our stars by name anymore. We have to look them up by telephone number or like 12-digit ID number now and hope that we get the right star. And we have to look them up on the internet through this machine. And again, this beautiful, incredible 8.4 meter telescope that will go online in about a year, year and a half. More stars than people in the galaxy. I don't know, that kind of blows my mind for some reason. So the job for us now has to change. So I started doing astronomy 20 years ago, back when we hit that ramp up, right? The 2-micron all-sky survey, 2MASS had just come out. Other digital sky surveys, USNOB had just come out. So we had just entered this exciting new era. And we had to learn what to do with these big catalogs. We didn't have any tools. We were astronomers. We spent all of our time studying physics, learning a little bit of math, trying to understand how accretion and gas and orbits work. And then you dropped this catalog that wouldn't fit on our ancient laptops. They wouldn't fit on there anymore. We had to change how we did astronomy. And we're having to keep changing it. Here's another good example of how the field is changing right under our feet. Here is the mentions just in the abstract of papers for the word algorithm. You can see its steady rise up over the last 30 years. And of course, the word machine learning, like the hype beast of machine learning, is exploding since like 2017. It's just completely exploding. Now, I mean, okay, these are not all papers. These are also posters and conference presentations. But this is anything that professional astronomers are doing and publishing and saving in the literature, mentioning the word machine learning. It's skyrocketing, right? The only tools we have to deal with this catastrophic amount of data is let the computer do it. And this is exciting, and I'll show you some examples of why I think this is really exciting and why we can do some cool science. But a little piece of me, I'm just old enough to remember, a little piece of me is a little sad about this, right? I'm a little sad that the next generation of astronomers may not have a favorite star. I mean, other than the sun. All right, so the field is changing. We're teaching differently. We're trying to integrate computer science into our classrooms. We have all these like astrostatistics, astroinformatics is a whole field. And even here at the University of Washington in lovely Seattle, where the cherry blossoms are out, you should come see it before they're gone. The Dirac Institute, the Data Intensive Research in Astrophysics and Cosmology Institute, not the Davenport is making Davenport is making asteroids more expensive institute. Increasing asteroid costs, that's what it was. I hope I'm not increasing costs. We have a whole institute now, which is a large fraction of our astronomy department, that is just focused on how do we ask questions of large data sets, particularly this new Rubin Observatory. There are now fellowship programs for graduate students, summer schools to learn advanced statistics, data science schools. You can actually go to Chile. This is a really cool program in Chile to learn statistics about stuff that will be done with telescopes in Chile. I love this program. We're having to change how we teach our students. Okay, so this provides an interesting opportunity. What do you do with 17 billion stars? Like if you are here because you thought the sun is neat, or because eclipsing binaries are cool, or pick anything you think you've heard of in astronomy, and now when you have 17 billion things, we've got like 50 or 100 or 10,000 of them now. It's all boring. Like nobody cares. Like, oh, you got eclipsing binaries? We have 50 million of them. Okay, so what? You like supernova? 10,000 a night. You like asteroids? We're going to double the population in the first 3 months that we know about. Well, I mean, which is good. These guys are going to like it. This is good. It's good job security for them. But like, you know, this changes our relationship with the field. So we have to change how we're asking questions. One way we do this is accept that the stars as a whole, the population, the demographics, if you will, of the stars that we see are telling us a story about our galaxy, a history of our galaxy, if you will. One example that's come out from the Gaia data that I'm very excited about, which makes me sad because I thought I had this idea of what the Milky Way was, and now it's shattered. Now I have to relearn it. We thought the Milky Way was like this big pancake or a pizza with like a grapefruit in the middle. We had like the little ball of stars, big plane. We live out here. Fine. Good. It's good enough. But no. Astronomers had to keep asking questions. We had to go take the Gaia telescope and map stars out 50,000 light years to the edges of the galaxy. And then we realized that the galaxy is not flat. It's warped like a Pringle chip. And we don't know why. I mean, we have some ideas. Something like 50% of the other galaxies that look Milky Way-ish, they show this kind of warp. Like, look at this. This is so weird looking. Something like 50% of the galaxies we see have this kind of shape. And now we know the Milky Way looks like this too. It's terrible. Okay, we don't quite know why it's this way. There's a couple of theories. One is that there's a bar of stars. We call it the bar. There's this large structure in the middle of the galaxy. There's craziness about orbital mechanics that can cause the galaxy to warp. But probably the answer, like we're all having beers here. I don't have to go on the record here. Probably the answer is that the Milky Way ate another galaxy. It collided with another galaxy, and that has caused this ripple, like a ripple in a pond. Something like that, right? It's a gravitational ripple. And it's not just that the Milky Way is warped like some weird cosmic Pringle chip. The whole outside of the Milky Way is a complete mess. It's a complete mess. It's not a nice, beautiful like distribution of stars that fades off and that's our galaxy, our beautiful, perfect galaxy. No, there's these big streams of destroyed other galaxies floating around in the outskirts of our galaxy. We call these tidal streams. You can see an example of this passing through the middle of our galaxy. Here's this line of stars that when you search for a particular kind of star, you can see there's like this big clump, there's a little cluster, and then these giant tails stretching 50 degrees across the sky at least. Huge chunk of the sky, this band of stars. And this is not the only one. They're all over the night sky. The Milky Way is a complete cosmic mess. What a disaster.